English. I'm third year undergraduate physics student. I want to welcome all of you here. I would like to start with thanking Radhika ma'am mainly for making this possible. We've been planning this for a very long time, and the whole physics week crew, they're all here. Okay, so yeah, we can start with. The first event is interaction with the professors. So I would like to ask all the professors to come up and just tell the students what your research is about and how you conduct it, and what are the applications and what is the implications of what you do. Okay, so a lot of us don't know right now what the professors are currently having their research on. So I feel this would be a great session where you guys can come and we can interact later on. So yeah, if any professor wants to come up right now, then let's raise his hand.
Let's start with Radhika.
That's not
Yeah.
So hi everyone, and thanks a lot to Neil and his enthusiasm for finally making this happen. We've been trying to get this done since December last year, I think. And physics week has shrunk to physics weekend, but it should be probably the beginning. We'll have better sessions next time. I think all the second year rights are here, is it? I mean, it's only the second year rights. Then there are very few second year rights. So normally, as I said earlier, we had these sessions where we would meet all the students and talk about what physics is about and all that. I believe we had an online session where we did something to that effect. But anyway, let's just, you and us talk together. So the physics department here is as old as the institute itself. I think 2004 is when we started, and some of us have even come down from the Pilani campus. And in the days of yore, we did teaching and we taught with our hearts and souls, and we did a whole lot of stuff about teaching, trying to improve pedagogy and so on. And I think around 2010, 2011 was when all of that changed. Until then, some of us were doing research, most notably PKD. He started and he continued, and he's still very active. He was like the research face of the department. And now all of us are trying to, keep up to this example. So I think after 2011, we have all kind of jumped into the research scene. Of course, what is very important is that, we have to continue to maintain our connect with the students, with young minds, the questions that they ask. It always keeps us, on our toes. And connected with that is the work that we do in the so-called higher physics context. We are, we do research in a wide variety of topics, and we try to bring them into the classroom as well. Personally, I started off trying to, study very abstract mathematical problems, but after joining WITS, I was very enthused by one of the most modern applications of the foundations of quantum mechanics. So currently, it goes by the broad domain of quantum computing, quantum information theory, and so on. That is basically something like a buzzword, and many different fields of research as well as thought come into it in this context of so-called quantum information theory. And it's a wide field of play for computer scientists, for quantum chemists, for biologists who want to use the techniques that we try and develop here. But for physicists, it's more like trying to leverage the most basic properties of quantum mechanics and come up with a new paradigm of computing, a new way to process information, which is different from what we've been used to so far. You all may be aware of the so-called weird properties of quantum mechanics, which include the superposition principle, the famous Schrödinger cat paradigm, where things are supposed to be quote-unquote alive and dead at the same time. That's just a very funny way of putting it, but basically what it means is it's possible to set up a system in such a way that, depending on the kind of observation you do on it, it's possible to come up in different final states with different probabilities, which is not true classically. Right? When you look at a ball which is supposed to be red, no matter when you look at it or whoever looks at it, the ball is red. But if you try to measure the spin of an electron, which is supposed to be either up or down, then depending on which particular measurement you choose to do, it will probabilistically come up as up and down. So this principle of superposition, as well as its extension, which deals with superposition of large number of systems which are coupled together, which results in a property known as entanglement, yields very strange kind of properties where you could make measurements on physically separated systems and yet get results which are strongly correlated with each other, without these two systems ever communicating with each other at the time of measurement or after. So that property, which is called entanglement, is also very strongly leveraged in this principle of information theory. Plus, of course, the fact that the experimental context is seldom ideal. We always have to deal with what is known as the system of, what is known as an open system. Okay, so in classical physics, we deal with errors and noise in measurement using statistical tools, and in a very rough way, statistical mechanics is the way in which we look at systems classically defined, which have a large number of components, all of which you don't have control on, and there are fluctuations, errors, and so on. This is particularly applicable also at the quantum mechanical level. And though we read our quantum mechanics 1 and 2 as if everything was very nicely, tightly sealed in the box of quantum theory, and we look at wave functions and we look at the evolution and so on, that picture is true only in ideal systems, not in the lab. The lab is essentially an open system which interacts with the entire environment, and there are various sources of noise and errors and so on. And dealing with this stuff and still making sense out of it is a very current area of research, which is known as the quantum mechanics of open quantum systems and the information content of such a system. So quantum information theory as related to open quantum systems. So clearly the maths of all of this is not going to be linear and simple. Mostly we have to resort to a lot of probability theory. And one of the latest players in this game happens to be differential geometry. There is a whole area of research in classical information which is called information geometry, where they deal with these probability distributions, different probability distributions as points on a differentiable manifold. And then you try and look at the distances between these probability distributions and look at their evolution as the system changes using the language of differential geometry. So my small team and me are trying to look at using differential geometry to characterize the states of an open quantum system and see if we can track the movement of this system by using differential geometrical methods. But prior to that, we just want to be able to describe the system as points on a differentiable manifold and to try and compare two systems. For instance, the input and output in a stage of quantum communication, for instance, these are two systems, and you want to say measure the fidelity of this process. How good was the output as compared to the input? Has it been deformed or has information got lost in some way? And to do this comparison, we wanted to use differential geometric techniques. How do you compare two quantum mechanical systems? How do you compare two probability distributions? So can we use distance measures and so on is what we are looking at, and it's difficult, but it's a fun task mathematically. Maybe my student will talk to you tomorrow about this. That's what I'm doing right now. Sometime in the last few years, I was also doing a small amount of research involving musical instruments, because apart from physics, the other passion I have is music. Because I come from a background where I have trained in classical Carnatic music, and there is this instrument that I'm very fond of, known as the Saraswati Veena. It's a very big and unwieldy and most unmodern kind of instrument, but its sound is pretty authentic and quite unique, is what I felt. So along with a colleague of mine in the mechanical engineering department, we decided to just analyze the sound, basically do a Fourier analysis of the sound and relate it to the structural differences in the Saraswati Veena as compared to a plain string stretched between two knife edges. So compare the sonometer sound with this Veena and see what are the modifications that you should perform on the sonometer to produce the Veena-like sound. Of course, the structure is different, but apart from that, it turns out that there's a subtle difference in the bridge that holds the string. So, unlike in a guitar where the bridge is kind of thin, or in a violin where the bridge is literally a knife edge, on the Veena as well as the sitar and tanpura, the bridge is very broad. So this breadth of the bridge, its curvature and its slope at the point of contact and so on seems to play an important role in the timbre of the instrument. So that was some of the research we have been doing, and there's a student of ours who's currently finishing up his thesis on that. But and then we used to run, some audit courses in music long ago, well before the pandemic came in, and there were a lot of students who were interested through the audit course in learning about the Veena and so on. Right now, unfortunately, they're not running. But we do have a room in the SAC which houses some musical instruments. Those of you who are interested could always go through either the music club or the community welfare, I believe, or the SAC, and go and tinker with your instruments. So thanks a lot for listening to me, and I hope you all get some of the excitement of doing physics and seeing physics in all the things that are around you, and just continue to be curious. Thanks. Thank you.
Is it presentation? Good evening. So, I think the separation is meeting, right? Okay, I think one of not. So I'm Prashant Kumar Das. So my area broadly actually I work in 2-3 areas, and that is the analytic physics, astrophysics, and cosmology. So my profile. Of course, more details you can get in my web page. So I joined the department I think 2007 July, and office D32018, and my phone, email, interest, homepage. I request actually each of everyone. Just I used to tell everyone this thing. Whether you are applying here, let's say you plan to work with someone. Whether it's this department, other departments, people, or anyone in the world. Okay. The first thing that you should browse that particular faculty web page. What you do, what you don't do. Sometimes you should not apply to a person who don't do working at all. Right? Because in your final year you'll be applying for your thesis and all other things. So your groundwork should be very robust. so that we should not waste your time, right? So only window that we have in a typical university or any research institute, that is our web page. Okay, so that is we always try to keep the dynamics with real information and up-to-date information. This thing, okay. Very useful information, and that you should actually keep in your mind. So this is my group. So, so from the left to right, Pushpita, I don't know whether these people are here. Anyway, so tomorrow there will be a presentation, I think, by the PhD student. Okay, two of my students actually will be speaking their work, and they will also update the work for other two people. So Pushpita on the, this to that, right? Left to right. Pushpita, then Shoman, and then Manish, and then Payal. So Shoman and Payal will be speaking their work, and also they will tell what their juniors are doing. So tomorrow is scheduled for that, right? I think that the time from 2 to what is it? Alumni talk. I think that is that will be allotted for also partly for the PhD student, right?
Yes, sir.
Because it doesn't mention. They are confused. What is that? Okay. So yeah. So two of my students will already been graduated. So Selva Garbati and Option this thing. So one is that currently Aisa Pune is going to join the South Korean University very soon. Another actually the Selva Ganapati was his first school at PRL, and he has applied to some other places, including where I think. Anyway, research interest. So if you look at so my work, okay, of course the details are there in the web page and this thing. So what I broadly work in areas for the high energy physics, they are actually very high. And I'll show one slide that you see that will summarize the interactivity that I'm doing currently. So high energy, how high it is, okay? And so as you know that actually your basic quantum mechanics essentially is telling somehow we can connect the time and the energy, coordinate and the momentum, all this thing, right? So as you will see that in high energy physics, so it is not like that only high energy physics, the cosmology of astrophysics automatically comes in. Because higher the energy, essentially you are moving backward in time. So when I'm talking about, let's say two particles are colliding, okay, at the very center of mass high energy, okay, that simply means we are in a position to probe the structure of the universe at a very earlier era. Okay, so for example, currently, what is the temperature of the universe today? Anyone know? The ambient temperature. 3 degree Kelvin around, right? At that amounts to 10 to the minus 4 electron volt. What is the temperature of the sun? What temperature of the sun? Not the surface. Anyone? Okay, surface 81, right? 6000. Okay, what is the core temperature? Any idea?
Some 15 million degrees Kelvin.
Yeah. So around this 10 to the 5 to the 6 degree Kelvin, right? Sun. So what are the energy at the time of Big Bang? Of the orbital incline, 10 to the 19. So that means, so when you're talking about, let's say, typically in the collider, then when you're talking about the energy, right, it's in of the order of tera electron volt. So 1 tera electron volt is equal to 10 to the 3 giga electron volt, right? And 1 GeV is that giga electron volt, 10 to the 3 MeV and so on, correct? So that means when you are hitting two particles very high energy that I'm talking about, so let's say electron and positron, let's say proton, let's say proton and antiproton, a very high energy, as I had of the order of TeV, essentially we are actually creating an atmosphere in the lab, the structure, the inner structure of the early universe. Okay, so if we look actually the what that actually I am doing it, so it has a three-prong activity. One is essentially the high energy activity, so high energy physics, where I do the colloidal physics. There are people in the department who do the string theory, all these things. We have Rudra sitting here. Okay, so they are essentially dealing with the energy, or let's say typical length scale, where the length scale that matters to them is 10 to the minus. What is the Planck length? Anyone any idea? 10 to the minus 33 centimeter. Right? What is the length of the human being? 1 meter is the order. Okay. So essentially, so when you are moving your journey from 10 to the minus 4 electron volt to 10 to the 19 G, okay, that's the Planck scale. Right? So that means essentially we are moving backward in time. So the journey towards backward in time is nearly fictitious thing. Actually, we are doing it in the lab. When you are hitting the temperature, let's say 100 GB, 1 terabyte, and this thing, we're essentially probing the different era of the universe. Some of these things I'll discuss. Okay? Right? So in that way, if you look at high energy physics, if you look at astrophysics, or studying the cosmology in the early universe, essentially they all are clubbed together. That is why people cannot isolate this high energy activity from the cosmology or from the astrophysics. It has merged. All these three subjects has merged in a single object. Okay? To know the truth, what is happening. Okay, at high energy, early universe. Okay, because today the temperature is very small. Okay, and also we will see that definitely that today the universe is accelerating. That also gives us something interesting. So this is broadly the things, and what I was referring is essentially this figure. I'll come back to the earlier slide. So this is the slide. So when you're talking about the time, so essentially let's say high energy is early time. So in the lab, when you're generating the high energy atmosphere, we have the information of early time, number one. And also by starting force, we go back in time. What do you mean by that is? So essentially, what we know today, the most of the what is called interaction that we see the presence of the interaction is the gravitational force at the large scale, as far as the interaction of the Earth, Sun, and the galaxy, this is concerned, or let's say the single photon, electromagnetic. We don't see the effect of the other two forces. You know there are four forces: strong force, weak force, gravitational force, electromagnetic force. The strong force or weak force essentially normally in the typical energy scale that I'm talking about, let's say 10 to the minus 4 electron, we don't see it. Okay, so we have to hit the particle or bombard the particle with high energy so that I can see those particles which are responsible for this weak force, and this thing we can see it. And W boson and other things. We'll discuss. Okay. So as I told you that we are living in a world where there are two type of particles are there, right? Spin half, the half integral spin, and the integral spin, right? So half integral spin that is essentially forms a matter. It's called the fermions. And how the fermions interact with the speed to each other, that is called a boson. Okay, those bosons are the force carrier. Okay, so there are four forces, right? So that respectively there should be carriers. Let's say electromagnetic force carrier is a photon that you all know, right? If there is the strong forces that binds that quarks inside this proton neutron together, that's called the gluons. Okay, colored gluon, all this thing. If you're talking about the gravitational forces, that's called graviton. Okay, and also you are remaining the weak forces. Let's say what is called the neutron decay or muon decay. So these are the decay which is carried by the weak force called the charge weak boson W plus minus and Z. So if you look at this table, actually I summarize the entire the structure, that means the matter and force carrier content in this table. You see there are quarks and leptons. Quarks appear in the three generations. There are 6 quarks: up, down, charm, spin, top, bottom, or a spin half. Okay, and quarks are most fundamental things. They interact with all possible ways: strongly, weakly, electromagnetically, and gravitationally. Of course, they have masses, so that it is gravitational. And also there are electrons, 6 electrons, 3 charged electrons, that is electron mu1, tau1, and the neutrinos. Okay, electron neutrino, mu1 neutrino, tau neutrino, and this thing. And the force carrier are this Z and W, responsible for the what is called the weak forces. Gamma is the photon, what is called the electromagnetic forces, force carrier, and the G for the gluon, strong carrier. We are not considering the graviton here in the standard model. It is just we don't do it because interaction states too small or weak. That's so weak. At this typical energy scale, you don't bother it. But you have to bother the moment you are talking about the cosmology. Okay, so let's say you are talking about early cosmology. Okay, where the energy typical of the order of it can be at the time of inflation, it can be of the order of m plane of several order m plane. We'll see these things. So these are the things. So this standard model essentially is a tool. It has a framework where all these particles, that's the fermions, fermions, and all these fermions, how they interact with each other in this possible manners, except the gravity. So it has been tested and verified experimentally. Okay, but this standard model, although it's experimentally successful, but still it has some issues. So, for example, it cannot explain features like neutrino oscillation. Okay, so that is unable to this thing. I think tomorrow in that presentation, some of these things maybe the students will explain it. And the dark matter, standard model does not accommodate any dark matter content. All these particles, that's normal, the baryonic matter or the normal matter. Okay, the dark energy. So that means this inefficiency, inadequacy, the standard model leads to forces us to think: is there anything something beyond the standard model? That's all we feel. So most of my activity essentially are in this area to look for astrophysical signature, cosmological signature, or let's say typically collider signature of this new physics. Okay, fine. So one of my main, so that was essentially the background. Sorry for the long illustration. I don't know how things, but anyway. So the first thing is that if you see most of the work, then I don't have these things. If you track the citation of a certain work in the typical high energy physics, you see most of the publication, almost 60 to 70% work in the typical high energy physics phenomenology nowadays comes in the area of dark matter. Dark matter and the cosmology dark energy is model. Okay, so almost 50 to 60%. Just check the archive. Anything. Okay, but anyway, so looking for this dark matter. So this dark matter, if you know that from the observation, that from there are several observations. Most famous observation is the WMAP CMS spectrum, which essentially the highest peak suggests that what is the content of the net energy of the universe. For example, as you know, that almost around 5% is the normal baryonic matter, like electron, proton, muon, all these things, right? Around 25% is the dark matter. These dark matters really they don't interact in the normal way that the proton electron do. They only interact gravitationally. Okay, and there's the dark energy. Okay, so as far as the estimation is concerned, 5% for the normal baryonic matter. Okay, the observable world. Okay, what is the observable world consists of this 5%. Only 5% of the net energy budget, and 25% is for the dark matter, right? So that we also don't do. We don't its mass, we don't its spin parity, but we can make a lot of speculation based on some existing theory. So essentially hitting hard to see that whether we can one day we can see the dark matter also in the collider. In the current collider, large hadron collider, upcoming collider, linear collider. So the showman actually presenting his recent work that we have communicated with the archive on the searching of the leptophilic dark matter in the linear collider context. Okay, upcoming electron position collider, center of mass is 3 TeV. So hitting this thing. Okay. So anyway, so searching for dark matter. So and to define not only colliders, there are indirect searches also. For example, xenon things that yeah, please.
So when you say,
Please stop it. Okay, at any point. Yeah, please.
so like when you say you want
Sit
to,
down, sit down.
so when you say that you want to cause these collisions in a lab and how to look at dark matter, what exactly do you mean here?
Yeah,
Are you looking at
exactly. Good point. The point is that first of all, as I told you, dark matter, just like a neutrino, it will act as a missing energy. So you cannot detect it because it does not interact quickly, strongly, electromagnetically, right? That is the only thing. But the point is that what you can do typically in the process, the associated particle. For example, whenever you are looking for, let's say, you have some model, okay? What are the model, this thing? So more details tomorrow. Suppose electron position collides, okay? Produce a pair of dark matter. How? That's an effective operator. There are two approaches that actually we are working on, the effective operator approach. So that will have a fermion on one side, have a fermion on another side. I'm telling, at some point of time, let's say when the universe was old, such that the energy at that point of time was 3 GeV, then these two particles, this dark matter, okay, and the normal standard model particle was in thermal equilibrium. Okay, actually same environment actually will be creating here. So let me go back, then I'll come back here. Okay, so that means I should be able to write down if an effective operator connecting this the final state fermions, there's the dark matter and this thing. Okay, so that is the Lorentz invariant operator that in standard field theory you can do it. Right? Question: how to detect? The detect is that we will not be able to detect directly the dark matter, but there are processes where there is associated production of photon, Z boson, H, and this thing. So normally, if you look at the normal process, let's say P plus E minus goes to P plus E minus. Okay, let's say typical Bhava scattering we are talking about with one photon or one jet or something. Okay, jet will not come here. Let's say monophoton such we are talking about. Let's say mono Z, Z boson or Higgs boson is coming out. So those processes, if it is purely standard model process, that will have a certain event measure, some certain cross section. But if it is a dark matter, depending on the dark matter mass and the scale that we are talking about, because we will be talking about effective theory. So it will be the event will be something different. So directly, you are right, we will not be able to see, but from associated production of this particular particle particle, which is a standard model particle, which you can detect in the detector, whether linear collider or higher, what is the LSC and this thing. Okay, so looking at this thing, production cross section or different distribution. Let's say photon is coming out. If it is purely standard model process, it should have certain energy distribution. If it is not standard model, let's say from something else origin, let's say photon is coming with a pair of dark matter, right? Some amount of momentum transfer will take place, right, between dark matter and this thing. So then there will be seeing that the dark matter mass, where the energy distribution of the photon in the two framework will be completely different. If it is purely standard model, one distribution, it is accompanied by a pair of dark matter, another distribution. From that actually you can figure out. So direct, there is no direct way of looking at it. It will be missing energy, just like a neutron. Okay? Is that okay?
Yeah.
Okay. Fine. So this is essentially the summary as for the dark matter structures. So this is the block. So essentially it depends on which way. So think about it. Let's say you have a thermal firewall, right? So where all these particles are there in thermal equilibrium, they stack it. Simple. Okay. So and the universe as a whole, let's say thermally isolated system, right? Now what I'm talking about, and that firewall was generated at the time of Big Bang, and the firewall eventually expanding. Right? Equilibrium is a standard particle, right? Dark matter. But after some time, what happened that the universe which is expanding. Okay, so that expansion rate, called the Hubble rate, maybe they're more than the what is called the interaction rate. The rate of interaction with which electron position collides into produce Sky bar. Okay, then those dark matter essentially will not be part of thermal equilibrium. Then they contribute to the another quantity of the relic density. So by measuring the relic density also you can hit the dark matter. So that is another way of looking at the dark matter. Okay, so that is essentially the indirect structures. This is we are directly producing the standard model E plus E minus to chi bar. We are directly producing the standard dark matter particle by collision. This is called the collider structures. Okay, and the indirect structures or another the direct structures essentially of let's say E plus E minus to chi bar. If it is a collider process, there are processes where chi bar goes to E plus E minus, so that will contribute to the relic density. Okay, so that is called the direct structures. And there are processes in the xenon where essentially one also consider the detection this thing. So in the xenon, this thing, so essentially you have a nucleon, proton. So the dark matter comes, interact with the nucleon, and it requires this thing. So looking at the what is called momentum exchange of this thing, you can also figure out momentum exchange what the required nucleon. It may be proton, neutron, depending on the detector. Okay. You can also see indeed it was hit by the dark matter. Right, so they are different. So that is this diagram actually summarizes this thing. So whether you are going from this to that side, or this side, so essentially it's the direct, indirect, collider side. This summarizes all this activity in the this thing, in the area of dark matter. Okay, become boring, right? It should be. Okay. Anyway, so this is. And also, that is one aspect. Actually, two of my students are working. That Shoman and Manish also will be joining. The new student. And another thing that I also work that is the, of course, that as I told you, that looking for the new physics. So that means the wave standard model. We know the some limitation of the standard model, which can be solved by beyond the standard model physics proposal. And there are a lot of proposals in the market. One is the idea of extra dimension. Okay, you're not living in the one dimension, only 4 dimension, right? 6 plus 1 dimension. It is there are more than this dimension. What you cannot see? Why you cannot see them? Because they are curled up in a so small circle, and the equivalent energy of that inverse radius is so what is called large actually, because energy goes on 1 over length, right? Correct. So that means so large, so small the length. Let's say that the entire universe. So that means to hit that length scale of extra dimension, this is curled up in a circle. You have to have the energy of as large as Planck energy, or maybe 7 order of TeV, which don't have. Currently, that LSC, that is the machine energies are around 14 TeV, the center of mass energy, of the 2 proton. Of course, at the quark level, there is parton level energy is around 3 to 4 TeV, it's much smaller. Okay, so we are far away. So anyway, the notion of the extra dimension, but its implication is very interesting. Okay. So, and of course, that extra dimension, the more than this thing, I think it regards what is called 10 dimension string theory. Okay. So, what I am talking about actually extra dimension, that is it may be one extra dimension, it can be also that 4 plus 1 extra, an extra special dimension I'm talking about. Okay. So anyway, so this extra dimension that is looking at the world is not made out of this only 4 dimension. It can be 4 plus 1 or 4 plus 6, 10 dimension, even at least things is on the polygon 32, no? 33 or 32 earlier without the supersymmetry. 23. Actually, 23. चलो 30 उल्टा हो गया. Okay. So essentially that notion of extra dimension is fantastic. It is the building block. It is at the basis of the formation of the string theory. Okay. So anyway, there are interesting what is called a study in the area of this thing, which was first proposed by in I think 19 I started so 1998, 1999. After them Diwali and Dimakolas and Ranasundar. So they proposed a host of models which are phenomenally very interesting. We look for the signature for at the colloidal level, not only astrophysical context, but on the colloidal level. Okay. So anyway, and also some area of the non-quantum space-time, because the moment you are talking about high energy, right? At the high energy, you know that then normally you know in your quantum mechanics that momentum operator commutes, right? Even position operator commutes among themselves, but position and momentum don't. But that high energy, when you're talking about SIS, let's say typically implant scale or very high scale, so then the momentum operator also don't commute. So space-time has to become non-commutative. They no longer become so commutative. So that non-commutative space-time essentially also may lead to the interesting features, the signatures that can be tested on the distinct. So people are actively doing it. Yeah. So there are these things. And all the signature for extra dimension, non-commutative or dark matter, all these things. So either you can look at for your art-based what is called laboratory. Okay, that is the what is called electron-positron collider. Electron-positron collider that I talk to linear collider optically, for large hadron collider, these things. Or you can look for the astrophysical laboratory. Let's say to explain some phenomena like let's say supernova cooling. Let's say 1983 cooling and the Rayleigh density criteria, 21st century cosmology, and all those things. Okay, so there are different avenues that you can test your idea. Okay, you can have your model, but the point is that your model should be testified by some things. Okay, at the colloidal level or at maybe the astrophysical problem. There are some problem barrier asymmetry which I have not mentioned. Okay, so you can test your idea whether your idea essentially can explain some of this problem. Okay, so anyway, so I also work in this area a little bit. So this is mostly collider and astroparticle physics. So this is primarily the cosmology. So I have another interest, some interest also in cosmology. As I told you, you cannot differentiate between high energy physics and cosmology. It comes together. Okay, at some point. Anyway, so in the cosmology, the area actually I am doing inflationary cosmology to understand several aspects of inflation. Okay, so it is very important because the universe that you see broadly in the large, let's say 700, what is called 100,000 kiloparsec or something. Okay, so the universe is isotopic and homogeneous, right? And if you demand the isotopic and homogeneous universe, okay, remember universe started. If we believe in the Big Bang cosmology, universe started from the zero size at t is equal to 0. The notion of time starts from there. After that, essentially, it's a fireball generated, and that fireball eventually expanded. And the expansion was isotopic and homogeneous so as to maintain that isotopic and homogeneity all throughout the time. Right? What are the footprints of isotopic homogeneity? That was there in the present CMB spectrum. And the CMB spectrum was originated by the photon, which were created when the universe was 350,000 years old. Okay. Right. So that means why the photons were created? Why the photon? Because when the universe was expanded, it was a plasma. Right? Let me give the big picture, then it will be interesting. So universe was expanding like a thermal fireball. Initially, it was very hot. Right? Everything was ionized. Or there's no atom or nothing. Electron, proton, electron, quarks, and all these things. As the universe is, let's say fireball is expanded, due to adiabatic cooling, the temperature, energy density falls down, temperature falls down. Okay, what happened when the universe was old, 350,000? Here, I think Z is equal to around 3,000. Looks like the redshift. What happened then? That recombination takes place. What do you mean by recombination? So that means the temperature falls down such that the temperature essentially the 3,000 degree. What is called temperature was 3,000 degree Kelvin. Present is 3 degree Kelvin. So what is happening that temperature is so small that electron and proton they have they are able to form a proton, or what's called atom, right? First hydrogen atom took place. There's the recombination. The moment electron and proton combine and produce that atom, so photon no longer be able to interact with them because atom is neutral. Photon requires the charged particle, right, to interact. So atom is neutral. So essentially they travel freely through the space, right? Because it's filled with hydrogen atom and all these things. Okay, those photons essentially travel freely. They form the same layer photon, and the temperature which was there at 3000 degree Kelvin, this is 3000 degree Kelvin at that time when the universe was 350,000 years old. Those photons now, the temperature of those photons is now 3 degree Kelvin. Why it is so? Because of the redshift, but because of the universe has expanded, right? It expanded means due to the scale factor. Whatever the scale is, so lambda should be scaled accordingly. Right? So whatever the at that point of time, if you look at the black body spectrum, if you map one of the lines with the 3000 degree Kelvin, that boils down to now 3 degree Kelvin of the black body spectrum. So that is my universe. But universe, if you treat like a small what is called the huge thermal fireball of size 10 to the 26 meter and this thing, different size if you look at it, such a Wikipedia this thing. So it is like that thing. So essentially we are at one of the black body spectrum of T is equal to, let's say, around 2.72 degree Kelvin, right? Right. So that means, anyway, so there are small amount of anisotropy because of the structure that has been taken. It is not entirely thermal fireball, right? A lot of structure, galaxy structure, and all this has been taken place in this thing. So that will amount to some kind of anisotropy. This thing. So those anisotropy essentially was listed here. If you see, when it's fully isotropic, there are complete orange things. Then the structure formation and all these things took place over a period of time, recombination, then after that galaxy formation. I think this picture gives it. Yeah. So this is the transition from the Big Bang to the current era. Okay. I don't know whether you can see it, each entry, but anyway, so that is the picture. Okay. So now, what I do? So if you look at this spectrum, so this is essentially the power spectrum. Okay. So the basic message, the key message that we are getting from the same spectrum is the W map, this thing, that the dominant peak that actually speaks about the net energy budget of the universe, dark matter, dark energy, and galactic matter. The second peak actually contains the relative size of the second peak contains what is the typical size of the what is called portion of the galactic matter with respect to the net energy budget. Second peak. Third and onwards speaks about the dark matter. Okay, so whatever the smaller amount of anisotropy that we are talking about, this is the anisotropy measurement. Okay, so that essentially, you see that you require the dark matter and this, because if you don't have the dark matter, you don't have the galaxy structure. There are many ways of looking at it. The moment you search Wikipedia, there's a dark matter, you will see the filament-like structure here and there. What are those? You have to define maybe the filament, the bright spot are different galaxies. This thing. And in between the dark spot, there's the dark matter. Because it's the dark matter that creates the gravitational potential well. And in that gravitational potential well, you are essentially, the matter is falling and from the structure. Okay, I think I have taken enough time, more than allotted to me. Okay, sorry. So anyway, so starting this thing, there is an alternate of the standard cosmology called the bouncing cosmology and this thing. So that simply tells that the universe actually does not start from the zero size. It has some finite size. Okay, so that is emergent and these things. Yeah, thank you very much. So any one or two questions? Because I have already exhausted myself. Yeah.
So you said that we need extra dimensions, but we consider them to be spatial. So why do we do that? Why can't we?
No, why the time-like dimension? That maybe you should the tachyon on this thing. Then yeah. Your question is why they are not time-like.
Yeah.
Yeah. So the issue is that if you take the time-like dimension, then there might be show the causality and something related things. So that is the normal. Whenever you require more dimension and this thing in your theory, and also there are the features of the tachyon things, which are physical, the negative mass square this thing. So these are the implications that you end up. That is why if you require extra dimension, your theory demand, let's say string theory. Okay, if you formulate the string theory in 4 dimension, it is null and void. You cannot do it. You have to have more than what is the 4 dimension. 1 time 3 space. Right? So then people try it. But we're talking time like this in try to end up with this problem. Then they talk about the space like this thing. And the importance of this space-like, why space-like? The thing is that the moment you work as extra dimensional model ADD, so the moment you are talking about your gravity, because if you look about the extra dimension, your standard model particle cannot go to the extra dimension, right? They're compact on this three-dimensional space that is called the brain. This is the brain that still people call, okay? Only gravity can go in the extra dimension because gravity is geometry of space-time. It can be 4 dimension, it can be 5 dimension, it can be 10 dimension, whatever dimension. Gravity is everywhere, everywhere. Right? So then the point is that the moment of extra dimension, while see that this higher dimensional graviton, let's say we have one extra dimension, the 5-dimensional graviton will see a kind of tower of 4-dimensional massive gravity. Normally gravity is massless, right? Gravity is massless, this thing, like the photon and the gluon. But you see that actually if extra dimension, the massless 5-dimensional graviton will be appear as a massless 4-dimensional graviton, that will be there. Because that will maintain your 4D general covariance, whatever, right? In the GT that you have seen it, right? Plus, in addition, there will be a tower of collision in gravitons. They are massive. So they essentially will affect in different processes. If you looking at the power scattering, E plus E minus E plus E minus in the LED model, then you will see normal graviton plus a tower. Normal graviton, if you look at it, the tank scale suppression, right? Coupling is very small. This is a 1/n plan. Just forget it. So what you have to do, but the moment you're talking about the tower, the effect of all these things, you will see the coupling of the order of the TV scale that you can throw in the collider. Okay. So that is essentially you can see. Sorry, I give extra answer. You ask about this thing. Yeah, maybe you can talk. Actually, maybe it's small question. Yeah.
It can be straight out from my side, but
I think it's silly. I think it tells a lot of things. Okay.
I just
You look at this point.
wanted to ask that when you were discussing about the collisions
Collision.
and all the data, so like are you actually performing the collisions of the scale of LHC because it's obviously not possible, or are you like extracting some?
Second question: are you performing the?
Are you actually performing the collisions of the scale of LHC or not? Are you extracting some data and are you running
Yeah.
simulations on the computer? So are you actually?
Oh no, I'm not doing. Okay. The point is okay. That's a very good question. Actually, what exactly I do? I as a phenomenologist, what I do? I don't have the experiment, right? Because neither the India can afford the LHC, right? More than 30 countries are involved in that this $3 billion project. Okay. What I do, the point is that, look, what LHC do essentially, they have experimental group do the data and this thing, and they share the data to the entire community. Okay. What I do actually, essentially, before they perform the experiment, we can simulate these things. Okay. What we do in the computer, we create a virtual atmosphere for the experiment. Right? Particles coming, they are colliding, they're just coming outside after the scattering, and they are going to be detected in the detector. And the detector, I think the showman will be telling tomorrow. Okay, in the detector, essentially, whatever the detector, those people, whether it is Atlas or CMS, whatever if it is LHC, of course, then the prescription that they give. For example, particles are coming out. Now, how those particles will be detected? They have defined the card. Okay, this should be the size of the magnet. This should be the size of this luminosity. All this factor, luminosity, everything. So those we take as input, and then with that input we take what will predict the number of events and the distribution, and that can be independently checked by because experimenters don't know the theory. Experimenters don't know something is coming. Let's say they know electron, positron coming. They know proton coming, but outcoming what is it? They don't know. It can be the signature of the dark, but it can be the signature of some other kind of new physics also. How we know? The point is that, but suppose you have a host of new physics model. Each physics have its own distinct features. There are some signature which is present for the dark matter, not present for the extra dimensional, uncommunity, unparticular, and also supersymmetry, this thing. There may be some signature for supersymmetry, not for others. So looking at those things, essentially, experiment is at the end experiment that will tell which theory eventually survive and this stuff simply. So what I do actually in the laboratory, in the computer actually create that kind of environment that actually experimental people will do in their experiment. Right. And by the way, these days they are largely applying this machine learning, deep learning, even the quantum computing. Because the data is so huge and this thing, and it's very horrendous thing. Actually, that I haven't mentioned, that's my future work, to have more informed idea about how to deal with this kind of deep learning and machine learning in analyzing this data. So anyway, that's I'm still learning.
So more detailed interactions can be had with the respective faculty members.
I think, maybe,
Saying that we don't have too much time.
Sorry.
We'll open the room for discussion with the professors later on. So right now
That's
have all the professors speak.
And not only discussion, you can directly send an email also sometimes. Because you have gone to everything, all part from okay. Okay. Sorry, I think I must be.
No, I don't want to bring the important thing is there's no question, no answer which can't be questioned, right? Alright, so, Neil, would you like to comment? Next.
Gaurav, this is huh? Sorry.
Guys, there's one of the quiz on what TKD
I have to stand here. Okay, I said something about the being for
Okay. We can shift it around if you want.
I prefer standing here rather than being here.
You can have. There's a chalk and all. You can write on the board.
Maximum teaching. Okay, well, thanks for organizing this. In fact, as I entered the lecture hall, I felt wonderful because the first time I was entering the lecture hall after the pandemic. So thanks a lot for organizing this. And let me just describe as briefly as I can the kinds of things I'm sort of interested in working on. Of course, except for teaching, which I think will remain my sort of first love. The idea of explaining physics and the idea of getting people interested in physics, and the idea of, in fact, getting people to think. Okay, that's the origin of any interest, to get people to think. Okay, so I often sort of describe the kinds of things which I do. Let me describe it this way. Now, this is an experiment which I've tried sometimes when I've talked about things that I do, basically classified as nonlinear dynamics and complex systems. Sometimes it succeeds, that experiment in a hall like this with an audience, sometimes it fails. So I hope today is the day when it actually succeeds. Okay, so normally the clapping happens after the lecture, right? After I've spoken, you are meant to clap. But let's actually reverse the order. So I would want you to, in fact, applaud. I want you to applaud my performance before, imagining that I just now either think that there's some extraordinary achievement which you want to applaud, okay, or maybe I've really given a great performance of singing. Let's make it classical singing, because I don't want rockers clapping. If it's a rock, if there was a rock concert, then you would clap very raucously. I don't want that. Okay, so it's like, just imagine it's an achievement which you want to applaud. All of you want to applaud as one together. Can you do it? Let's see if you can all applaud as one. So now you can start. Paying attention. It wasn't the best of the claps that I was trying to collect together, but you may have noticed, although there was some distribution of claps, but over a period of time, your claps sort of converged. And there was a degree of coherence and synchronization in your clapping, which you may have heard. It wasn't, like I said, the best of the clap. Sometimes, it really happened all at once. And you would have, in fact, witnessed that. Okay, all of us have witnessed that. Now, how does that actually happen? So that's sort of emergent behavior, that's called as collective dynamics, things which there is nobody whom you are following. I wasn't trying to tell you what pace to clap at. All of you were clapping at your own pace. But nevertheless, somehow, through magic as it seems, all of you started clapping together. Now, how does this actually happen? Now, this is an experiment which I've been trying to do to understand this through a set of students over a set of last 3-4 semesters. Since the various hurdles which we have faced in doing these experiments, every semester we remove one hurdle, but a new one sort of comes. So we haven't sort of got to the answer. But the question is the following. The question is, what conditions, or what are the minimal conditions required to bring this about? bring this synchronized clapping about. Here, all of you can hear each other. Okay, all of you are sort of seated at different distances, so maybe you can hear your partner better than what you can hear somebody far away. But all of you can sort of hear that collective, clapping which is going on. But supposing that wasn't possible, suppose we set up an experiment to create conditions which would break this by getting some of you to only be able to hear some others. So we set up a network of clappers. It could be a square network, it could be a ring network, it could be some networks, and see whether on those networks, whether synchronization would be brought in, and if not synchronization, there could be a variety of other collective states which can be brought about. It could be some kinds of waves, it could be anti-synchronization, it could be no synchronization at all, or other things could happen. These are things which are found to exist in variety of other systems which are different from the system which I'm describing. And therefore, one would want to know whether all that can also happen here. So the other thing which I like, when I was telling you, the other thing which I sort of told you, square networks, ring networks. So we are changing the topology of the network. So thereby meaning that the topology of the network will have a determining effect on the kinds of dynamics which will be witnessed in the system. Right. So therefore, topology plays an important role. So exploring topology becomes a very important aspect of the kind of work that I'm sort of interested in. So where else does this come in? Where else does this kind of phenomena come in? So let me give you another example, and that's why I sort of started.
Is it the bridge? The swaying of the
Yeah, bridge is another one, but I won't give you the bridge as an example. Okay, this is another one which I like to give, also because okay, now, okay, I'll tell you what this is. This is a metronome, essentially a pendulum with a source of energy. So you have to wind it and then you let it go. Okay. Now, well, those are musicians who know what a metronome is. Okay. Then nevertheless, so let me just. So this is an experiment. Okay, are these people? Okay. So in place for the folk can, support all of them beating separately. That's like the synchronous clapping that we were talking about. All of them start beating together. Okay, that's synchronization. With different conditions, if you probably made the surface slightly wet or some other thing, or change the mass, there may be an anti-synchronization, something else to happen. Sure, okay, not just this. So this is another example of sort of synchronization. The dynamics would also depend on if you here every metronome is connected to every other metronome. It's like coupled. These are like coupled oscillators, which you do in mechanics oscillation and waves or classical mechanics courses. But these are not the traditional linear coupled oscillators. Linear coupled oscillators in some sense are boring objects. All that they do shows just the normal modes. That's it, and nothing else. Non-linear oscillators have a variety of very rich features, which and lots of different possibilities, sort of come about. And synchronization, the collective dynamics is sort of one of them. So Yashi, where is Yashi? Yashi was. I saw Yashi walking. Yashi not here. Okay. Yashi was doing. Last semester he was doing a much simpler kind of simulation. So I don't really do experiments except for the clapping one was we were trying to do an experiment. Mainly do the simulations. So he was trying to do some simulations involving metronomes, but on the swing. And he got some interesting results. But at the end of it, we actually halfway through we discovered that the equations didn't really describe the system that we thought they were describing. So then the problem really boils down to actually looking for a system which is described by an equation. Okay, which would show that interesting behavior that we thought it would. So one kind of systems which we thought possibilities like electrical circuits or something, but neither myself nor Yashi sort of knew much about that. But I'm sort of trying to describe to you systems where which show this kind of emergent behavior. The other kind of systems which exist are which often I sort of get interested in are in fact is the brain. The brain is contains it's a network. What is it a network of? It's a network of neurons, and neurons has dynamical elements which change. Whose things are changing with time. Okay, so what changes with time? It's the membrane voltages across neurons which actually change with time. They form an action potential. So if I prick myself, there's a change in potential, and then the change in potential travels as a wave down into the brain, and sort of things happen, and then you respond. So now the fact that when you prick and a wave gets created which travels down, it's possible only because neurons are actually nonlinear creatures. The dynamics of neurons is determined by nonlinear equations. If it wasn't, if they were linear equations, pricking would really have no effect. There would be nothing traveling down to the brain. So your brain is a network of neurons, and neurons in the brain also synchronize. Amongst other things, it's not necessarily. I mean, there is some collective motion that they show, given the right sort of conditions. Sometimes things go wrong, and there's over synchronization when you don't want synchronization to happen. So then people get those epileptic fits. There's a high degree of synchronization in regions of the brain where you don't want that to happen. On the other hand, when you're asleep, there's a certain sleep stage called NREM. And in that stage of the sleep, there are a large population of neurons within the cortex, which simultaneously, they become very active. They fire a lot of action potential. Membrane potentials are changing very rapidly. All together, it happens to all the neurons, a large population of neurons together, and all of a sudden they fall silent. Okay, so this is again sort of synchronization in the brain. Now, synchronization in the brain is also important because unless things synchronize together, how do you sort of make sense of things which are coming through different sense organs? It doesn't sort of seem so. There has to be a degree of synchronization. The question is how that collective things at the right time, how they brought about together. And topology, of course, must play a role somewhere. The kinds of entities, there are a huge number of neurons. What essential features of neurons would make that happen? That will also play a role. So in fact, there are different kinds of neural circuits within the brain. Okay, so Abhay, who's there? Abhay is there. Abhay is in fact identified a couple of neural circuits which are called as motifs. Motifs which are patterns which get repeated in the brain, which very small neural circuits, just containing 3 or 4, 2 neurons or 4 neurons, and trying to determine the dynamics of these just a small unit of neurons. Would the small unit of neurons synchronize, and when will they synchronize? So there are different kinds of synapses, excitatory synapses, inhibitory synapses. There are different time scales involved, the different strengths of interaction actually involved. So all of this. So what kinds of conditions would in fact yield synchronization or something else? Okay, so that's what he's sort of exploring. But then you can also put a large number of such things together, which make it more real. Let it represent some part of the brain, the neural circuits in some part of the brain, and then again ask the same question: what would happen? And often funny things happen. So one of the funny things which sometimes happens is supposing you have identical. Now this is a more general thing. It's not necessarily neurons alone. Supposing there are certain states called chimera states, which are symmetry breaking states. What happens there? Everything is identical. Supposing all those entities which are rhythmic entities changing with time rhythmically. They're all identical. They're all interacting with each other identically, but their behavior isn't identical. So what happens is that it could happen that supposing all of you are sort of those rhythmic entities, maybe neurons or something else, or maybe metronomes. It happens that some of you over here are, let's say, supposing you were clapping, you all clapping together, but some set over there isn't clapping together. They're all clapping asynchronously. Even though everything is identical, all of you are identical, interactions are identical. So those kinds of things also exist are believed to exist in the brain. I mean, it's believed that something called unihemispheric sleep, which is found in the birds, where the birds actually can sleep with one hemisphere is asleep, the other is awake. Okay, so it's believed that, and what you find in that state is that the state which is asleep, that's very active, and the state which is awake, that's less active. Okay, so it's in terms of synchronization. So it's believed that it could be maybe a chimera state of a kind. Uh, but anyway, so what I would also be doing is to in fact explore synchronization in certain neural circuits. Okay, that's another thing. Okay, so well, I'll probably so that hopefully gives a flavor of things which interest me. Okay, and of course, there are any questions we could discuss out. Okay, I guess when we have a cup, when we is I don't is there a cup of tea?
Yeah,
Okay, thanks. I was about to say a cup of tea, but I wasn't sure whether there's one. Okay, so we could discuss talk outside with a cup of tea. Okay, so thanks.
AVK sir, if you want. Yeah.
I mentioned cup of tea and I was not tea.
It's a fight.
I was wondering if there are some samosas there as well.
It's a big secret.
Can stand and speak anywhere.
Yes sir, anyway.
But generally, all this high-tech environment sort of phases me. I'm somewhat of an old-fashioned Luddite. But nevertheless, I think I believe that technology does increase convenience, and I think the convenience probably attracts people more than. But of course, people who have to set it up, they are going to be in dire need because nobody else can do the setting up. So anyway, let me talk a little bit about myself. I think I'm notorious for various reasons, but perhaps I'm sure that people will look kindly upon my efforts. I have been interested in teaching for a very long time, and that has sort of been default. What has happened is that I've sort of swum against the current, try to understand things entirely through my effort. And then I find that, look, I put so much effort in learning and doing things that it would be an utter waste if it were to all remain within me and not be exposed to the students. So it's more like sharing what I have is what has probably made me an ardent teacher. And of course, my teaching style and everything is a little bit different because I teach students the way I learned it, which is probably not the way that books are written or probably the way that curriculum is designed. And so therefore, I'm always the odd man out. Okay, so I'm sure many of, I don't think I've taught any third yearites for a long time now. Have I? No, I don't think so.
So you took our whole year.
New faculty members have taken up that entire. So after that, I think I've been mostly involved in some PhD courses. So some of the PhD students may probably agree or disagree. I don't know. So anyway, that is as far as my teaching is concerned. I joined BITS Pilani in the Pilani campus in 1995, November of 1995 or 96. November of 96. And I spent roughly about 8.5 years in Pilani, and then I came here to Goa to open the doors of the campus, which means I was here since 2004 and I've not gone anywhere else. So all these years I've been only in Goa. And I enjoyed my work when I got here, and of course they thrust a whole bunch of administrative stuff on top of me, and one of that involved interacting very closely with students. And for a while it worked, but after that it was a disastrous failure, as I'm sure you must know from the annals of history of the Goa campus. Okay, so it will be written in red letters long after I've gone from this place. So anyway, apart from that sad chapter in my life and perhaps in the life of some of the students here, I focused primarily on teaching physics. And of course, research was still not a priority. And as Madam Radhika pointed out, it sort of began in 2010 and 2011 as an organized activity of the department. Prior to that, it was primarily an individual activity. And while I was certainly interested in doing research, I found that both the infrastructure and the amount of time that one could allot to that activity was very limited, because in those days teaching duties were quite onerous and quite heavy. They are even today. That's because people have differing standards of teaching. If I struggle myself, if I struggle to teach very hard, it's because I've got a different set of standards that I answer to, which are not necessarily required by the administration. So I'm still struggling to teach, so to speak. But then research is becoming an important component in almost every faculty member's life here. And for some, it's probably going to be their entire life. Their life is going to depend upon their productivity in research. Fortunately, I sort of escaped that glare that one would be subjected to, and I received my promotions probably based upon my teaching abilities. So anyway, I've been a professor here for the last several years in the department, and I teach mostly subjects which are associated with the sort of classical portion of the physics. I've taught quantum mechanics, however, but I've taught classical mechanics several times, classical electrodynamics I'm currently teaching to the PhD students. I've taught electromagnetic theory. I've taught almost all subjects that the department has to offer, except for two, I think. The two subjects I have not yet taught are the solid state physics and atomic and molecular physics. So these are two subjects that I have not taught, but barring these, I've taught everything. I've also taught all the labs. I think there's the Morphy lab and there's an advanced physics lab, I think, APL. Okay, I have not yet taught APL, but Morphy lab I've taught, physics 1 lab, physics 2 lab I've taught. So I think I've taught most of the courses that the department has to offer. I've also taught courses outside the department. I've taught complex analysis for the math department fellows. I've also taught a course in nuclear engineering to the chemical engineering fellows. And I was also a very popular teacher for engineering thermodynamics. I call it engineering thermodynamics. People just call it thermodynamics for the mechanical engineering department. In Pilani, I was the IC for that course for 3 years running. And I also wanted to teach electromagnetic fields and waves, but I think the gentleman who was sort of in charge of those things said that I was not a good enough teacher because I thought that the textbook they were using was junk. So the moment he heard that statement, he said, "Oh, you can't teach that." So I not had the opportunity to teach electromagnetic. And subsequently, one of our physics faculty members was able to teach it, and he did a very good job. So he stuck with that course until he got bored of it. And now there are sufficient number of people in the electrical engineering department. Okay, coming to research. I have been interested in at least about 2 or 3 problems. Okay, I have got a PhD student who is working on this area called the scanning tunneling microscope. And let me relate an anecdote as to how I got into this subject. When I finished my PhD from the US and I came to India, for about a year or so, I really didn't have a job or anything like that. I was applying here and there, but as you know, people don't respond immediately. It always takes 3 to 6 months before you get to hear that they don't want you. So meanwhile, my brother had just finished his PhD from Pune University, and he had a lot of friends, and some of them visited our house. And they happened to see me sitting idle. They said, "Why do you sit here idle? Why don't you come to the university?" I said, "Fine." I went to the university, visited with several faculty members. They were all very kind, of course, talked to me, but they realized that I didn't have a position, and they lost interest in me. Except for one person called Chandrakant V. Dharmadikari, who had a STM lab. And I said, "Is there any place I can sit?" He said, "Yeah, you can take this stool and sit here in my lab." So that was the only place he had. So I sat in the lab and I saw his students work scurrying around. It is an experimental facility, by the way, and I'm a theorist. Okay, so I looked at it and I got interested in the subject, and I coined my own title for that work. Basically, an STM is a scanning tunneling microscope. So it's basically a very sharp tip, so that the tip size is angstrom level, and you bring it very close to another conducting surface. Okay, and then what happens is, because the potentials are so large, you can have tunneling between the tip and the sample. Both have to be conducting. Okay, and this tunneling current can be measured. Okay, it is of the order of picoamperes, nano to picoamperes. And this current depends very sensitively upon how high or low the tip is compared to the sample. Okay, and it turns out that it's extremely sensitive because the dependence is exponential. So if I then move the tip along the sample, there are going to be ridges and dips and dimples on the surface, which can be detected by changes in the tunneling current. So if I take the data of the tunneling current by raster scanning of this tip, and then I project it onto the screen, I'm actually able to see atoms. Okay, and this tunneling is a quantum mechanical phenomenon. What I'm measuring is current, which is a classical quantity. Of course, the current that I measure goes through an amplifier and all that. The electronics I don't fully understand. Okay, so I'm measuring a classical quantity. But the phenomenon here is quantum mechanical, okay? And what am I observing? I'm observing atoms, which are really the regime where quantum mechanics works. So there you have it. Quantum mechanics with classical hands. I can touch and feel quantum mechanics with my hands, which are classical. That's what interested me, okay? And I said, well, how do you calculate it? I mean, how does one predict what should be the current? So I learned with a shock that nobody knows how the current actually flows, right? So there is a certain theory that does it, which is called, what are those fellows' names? Since I don't like their theory, I don't usually remember them. Okay. But it is the most popular theory, okay? And it's very complicated. But I suspect that theory works when the tip sample distances are of the order of a fraction of an angstrom, such that the atomic orbitals overlap. So there the tunneling actually happens between two atoms. However, if I move the tip further up so that there is no overlap of orbitals, then it is going to be pure electromagnetic fields that are going to be acting. Actually, it's mostly electrostatic fields. So I said, okay, let me move the tip further up so that I don't have to worry about this quantum mechanical complication of overlapping orbitals, because that means I would have to study atomic theory and molecular theory and all of that stuff. Basically, I would have to do a bit of chemistry. Very difficult for me. So I said, okay, let's pull it up, and then we can look at a classical picture of how the fields are configured, because that is just simply a boundary value problem. Okay, and once I know what the fields are, then I go and do quantum mechanics to find out what would be the tunneling probability for electrons to tunnel from the tip to the sample. I take minimal assumptions regarding the structure of the tip and the structure of the samples, because these, of course, would have to be relevant. But I asked around people and they said, oh no, everything on the surface looks very much like what it is in the bulk. So you don't have to worry too much about it. So I'm not worrying too much about it until a referee says that, oh no, we have to worry about it. So far, nobody has said anything. So we are going to continue with this. So this calculation is almost complete. We are now trying to construct a calculation for these things. And the original calculation involved planar surfaces. That is, they didn't have tip and sample. They simply had two flat planes, and there was tunneling happening here. So the question was, okay, if I know what the separation is, how do I find out what is the tunnel current density? Because if these are flat planes, the current would have to be infinite. Right? But so I cannot calculate something that is supposed to be infinite. I can calculate the current per unit area, the current density. But what do I measure in the lab? I measure currents in the lab. So how do I go from current density to currents in the lab? Well, in the lab, they don't have flat planes. I thought of actually doing an experiment with small sized flat planes put together close by, but you cannot achieve separations of the order of angstrom separations. The most you can get is micrometers. And then it turns out that the response is mostly an ohmic response, which is not tunneling based. So therefore, that experiment couldn't be done. So we had to somehow convert this information of tunneling current to the current. How do we do that? Well, you find out what the field lines are. Then you assume that the small portion of the surface that is emitted from that field line, and the field line comes to the sample over here. These two pieces constitute flat planes, and the separation between these planes is going to be the length of the field line. So you can do an integration of the field line, and then you find out that you can actually calculate the current, provided you limit the number of field lines coming out, because when you are very far away from the sample, then of course the effect is going to be negligible. So therefore you can actually use this field line based calculation in order to find or convert a planar model current density into a measurable current, which can be measured. So that we are trying to put finishing touches to that calculation. There are a variety of them. So that is one of the problems that I'm interested in. And my PhD student is almost about to wrap up that. The other problem that I got, by the way, there is an anecdote associated with the second problem. When I was, like I said, when I was unemployed, when I came back from the US, so I was also trying to do various things. There was some gentleman called Dhurandhar in Ayuka. I don't know, some of you may have heard. Okay. He was one of the original people who was trying to push for detection of gravitational waves. Okay, in those days, gravitational waves were mostly theoretical idea, and I think the only experiment done was the Weber cylinders, giant cylinders. So he was looking for somebody to work with him, and I applied. Like of course, you apply everywhere. Although my subject was nuclear physics, okay, I said I can do your work. And I think he talked to me over the phone and he said, "Man, I already have someone. Apparently has already found someone." So that's okay. So that was done. And then what happened was I'm also a member of IAPT, Indian Association of Physics Teachers. And they called me out to give talks or something like that. And I was there at one occasion. And Dhurandhar was there too. They had called him to talk as well. So we got talking to each other and I said, you know what, I had applied to work under your guidance for as post-PhD and you didn't take me. So now I'm into teaching. If you had taken me, I would have done research in general relativity. I said I've taken courses in general relativity. I'm terribly interested in it and so on. So I think, I don't know, he was struck by that. I mean, he felt bad perhaps. So he said, look, I'll tell you what I will do. I'm going to call you for a collaborators meeting in Ayuka, okay, where you can interact with people who are going to set up the LIGO. The LIGO is the Laser Interferometer Gravitational Observatory. There are 2 or 3 of them elsewhere in the world. They wanted one in this part of the world so that they could do triangulation and detect more parameters of gravitational waves that could be detected. So here the idea was basically you are going to have 2 objects that are going to go around like that, and eventually they are going to keep coming closer and closer and crash into each other. Now as they are coming closer and closer together, you can see that their quadrupole moments change at a much faster rate. So they have got a very fast changing. That means the rate of change of the quadrupole moment is very, very large. And when that happens, gravitational waves are generated. So what happens, you are going to have the slow spiral, then you are going to have a fast one, and then you are going to have a collapse. Okay? And then after the collapse, the whole thing becomes a spherical body, quadrupole moment disappears. And then what happens, you are going to have a ring down. That means it's going to quieten down. This entire process takes place in anywhere from a few seconds to maybe a couple of minutes. Okay, and the amount of energy that is released, if you calculate the gravitational energy that is released, that energy is larger than what is generated by the entire galaxy. But it's not in electromagnetic waves, it is in gravitational waves. Okay, that is what is very interesting about it. And in addition to that, if you look at the power spectrum of that particular energy that is generated, if you look at the power, because it is so much energy is put out in so little time, that power is much larger, or at least comparable to the power that is generated by all the luminous bodies in the entire universe. But it doesn't last that long. It lasts only about, at most, from few seconds to a few minutes. So whatever you want to observe, you have to observe during that short time. And you have to identify the parameters of these colliding objects in that short time. So what do you do then? How do you find out the parameters? You've got such a short time to look at it. So what you do is you observe the gravitational wave parameters, and from the gravitational wave parameters, you have to infer the properties of the orbits and the parameters of the collision. So what you do is you assume a variety of parameters. So you are going to have a space of parameters. And for each point in the space of parameters, you find out what is the pattern of the gravitational waves. So you develop what is called as a template. So what you do then, for each point in this parameter space, you develop a template, and you are going to create a bank of templates. So as soon as some data is coming in, you search this bank to see which is most appropriate. Okay. Now, why is it that I cannot take just one or two templates and say, oh, well, if something is here, let me interpolate between them? I cannot do that because gravitational field equations are nonlinear. And nonlinear equations mean that each set of parameters requires its own solution. You cannot arrive, very accurately at least, the solution for a different set of parameters from one set of parameters. So you have to have these template generations. So now it has so happened that LIGO is a very, very old idea, right? And there are a lot of template generations that have already been done. So now the idea is how to make a quicker match of a given data with the template. Imagine the given data is noisy. How do I know that a certain peak in the noise is not actually a facet of the data? So you have to do a lot of proper data analysis in order to see how to match a given signal to a template and extract meaningful parameters from the observational data involving gravitation. So that is the second problem I was a little bit interested in. But now it turns out that most of the work that remains in LIGO is mostly data analysis. The physics part has almost all been done. Okay. However, there is a related problem called LISA. LISA is that, well, I'm looking at slow in spiral. So I'm not looking at any dramatic events like collapse or crash or something like that. Now in the slow impulse, you are going to have a lot of time for these objects to go around. Actually, usually that's what happens. So we are looking at, say, two black holes going around each other. Okay. Now what happens there? There is going to be radiation, gravitational radiation. And this gravitational radiation is going to extract energies out of the rotating bodies. And what happens? They will no longer be following geodesics. They will be deviating from their geodesics. Okay? So from the gravitational radiation, can I find out, okay, what is this deviation? And since these are two black holes going around, they are going to have an effect outside their orbits as well, their gravitational field. So I should be able to predict what will be the change in the gravitational fields of this rotating binary, okay, outside of it. That means I can confirm several things. I can confirm how much deviation is actually occurring and how is it correlated to the gravitational wave that I'm going to observe. And further, I can also confirm it by looking at what are the effects of this change on the outside environment. So this is primarily a gravitational field radiative reaction problem. This problem is terribly interesting. It is interesting probably from the application point of view that you can do so many things. But it is interesting primarily from the physics point of view. Okay, there are many very, very interesting. The simplest example would be your hydrogen atom. The electron goes around it, and classically it cannot survive. Okay, but the calculation of the decay of the orbit, the classical calculation of the decay of the orbit is very interesting and very difficult to do. Although some people do some back of the envelope calculation and they come up with some number like, oh well, an atom would not be able to survive for more than 10 to the power minus 8 seconds or 10 to the power minus 16 seconds or something like that. Okay, but an actual exact calculation is not so easy to do. It has been done, by the way, but it's not so easy to do. A similar calculation involving gravitational waves is even more complicated. Okay, and it is just that sort of a complication that I would like to sink my teeth into. Okay, so I'm looking for people who can help and work with me. So I have a PhD student who is likely to take up that problem, but we don't know. We'll see what happens. So these are three problems that I'm interested in. The fourth problem, which is not really going anywhere, is that I'm interested in foundations of quantum mechanics. Radhika mentioned that she wanted to leverage some issues in foundations of quantum mechanics to do something interesting, okay, such as run a quantum computer. My interest is not interesting at all. I don't want to do anything. I just want to think. So I'm interested in foundations of quantum mechanics because I'm interested in foundations of quantum. I don't care whether anything useful comes out of it. So the fundamental problem that I'm interested in is that quantum mechanics, as we know, is non-local. Okay, I want to find out exactly where is this non-locality coming from. Most of the discussions of non-locality in quantum mechanics involve systems which are non-relativistic. And I'm going to claim, okay, anything that is non-relativistic is probably not going to obey the laws of relativity. So that's no surprise. The point is, okay, let's take a look at relativistic quantum field theories. In relativistic quantum field theories, I know that covariance is built into the subject. Now my question is, where does non-locality come from? Because the fields, when they are quantized, do satisfy microscopic causality. So my hope is to try to understand non-locality or even lack of commutativity or something like the, what experiment is that? EPR type experiment with quantum electrodynamics, for instance, to try to understand where the non-locality actually comes from. So this is just an open-ended problem right now. I have not succeeded in doing anything with it so far. Okay, so I think I've said all I wanted to say. Thank you. Any of you have any questions, you are certainly welcome to talk to me later. Thank you very much.
Terry, ma'am.
Hey, good evening, everyone. I hope you are enjoying the class. So I'm basically working in the area of experimental Handel's matter physics. So more precisely on semiconducting thin films and their applications. Also semiconducting nanoparticles. So what we do is we actually fabricate semiconducting thin films in our lab
When you say thin films, it is of the order of the films which we fabricate are of the order of nanometers or micrometers. So we deposit and we can manipulate the properties of these thin films. And when you go to the nano regime, you know the properties from the bulk very a lot, right? When you go to the nanoparticles. So how does these properties change? How can you manipulate the properties? How can you fabricate or deposit these thin films? I mean, basically, we are doing. I'm working on metal oxides and metal sulfides, semiconducting sulfide materials and oxide materials. So it's one area. So we are also trying to find out what are the applications in devices like photovoltaic cells or UV emitters, photodetectors, gas sensors, and things like that. Another area in which I am interested in is diluted magnetic semiconductors, where you can actually manipulate. I mean, you can induce the spin degree of freedom into a semiconducting material. Like you can keep your semiconducting properties of the materials intact by and you can induce magnetic properties by various ways. Okay. So that is actually useful in spintronic devices, spin electronics. Spintronics is basically spin electronics. So one of my students graduated in that area. So what we are trying to do is we are using simple semiconducting, oxide materials and trying to uh, manipulate, add impurities so that we can use magnetic properties in that. So these are the broad areas in which I'm working on. So you can come and see the lab. We have some facilities and you can use them. Right? So this is the semiconductor devices, and so we have separate labs now in the new building. So this is our semiconductor materials and devices lab. Okay, you're welcome to. I think there is an interaction section tomorrow, right? For lab visits. So you can see the instruments and we are basically, it's like you would have heard of all these things, and you are studying, right? Semiconducting materials or devices and their properties. But doing it hands-on is, preparing your own materials and devices and measuring their properties, that's interesting. So, yeah, come to the lab if you're interested. You can talk if you want. If you want to discuss anything about that.
I think those lab sessions are planned, right?
We'll
We
have
had these detailed lab tours that
Yeah.
PhD scholars can do probably next week. Is that what you're
sometime next week.
Yeah. So those will be really focused on the labs and what people will be doing.
Okay, so if you are interested, you can come. Anyway, the lab visit is there, but otherwise, if you want to talk to me, you are always welcome. I hope you know me. I don't know. I have done some some familiar faces. We have done some labs together. But now always everybody wears masks. So it's difficult. Okay, thank you.
Thank you. We're getting the snacks soon. We can have one more professor, then we can continue after the snacks. So, who wants to come maybe?
Needs chai person. Chandra doesn't need chai. Chandra lives a rare. Huh?
Okay.
Okay, great. He's making way for you. You don't need to get up. Great.
Good evening, guys. My name is Raghu. Most of the department calls me Raghu. I've been with the campus since 2005. My background, my training is in the area of high energy physics, and I mean, I've taught a variety of courses over. I mean, I've been here for a little over 15 years, and I've taught a variety of courses, in the department. But over the last few years, I have kind of settled into teaching atomic molecular physics. That's one course, VK said as he has never taught. Right? So I've been teaching that.
And he is the one who taught electromagnetic fields and kept that course away from me.
I actually didn't think of it that way. By the way, people might even still be interested, in you going to teach that course if it means it spares a few
they
people.
Look at my name and they say nothing doing.
No, it's just that now I think the department has specialists in that area. I think if I were to request for, they'll probably send me kicking back. Yeah, so I have been doing atomic molecular physics, and well, depending on students' interest, I also run this course on quantum field theory. That's personally a big area of interest for me, and that's one of the reasons I do. So usually, even if there are 4 or 5 heads who are deeply interested in doing it, I definitely find time to teach that course. Other than that, I have been kind of steady with the electromagnetic theory course. I mean, I just love that subject. Part of the reason for my own interest in it is that it's one of the simplest examples that you can introduce, of a theory at an early stage. People get exposed to it right at the high school level itself. And it's one of those subjects whose entire physical content can be summarized in a set of few equations, and those equations, with the ability to compute that we have today, we can do amazing things there. But those equations also, display. By the way, that particular theory is also what is called as a field theory, because the basic entities are fields, right? But the underlying principles are those of classical mechanics, so we call it as an example of a classical field theory. But when you study classical electrodynamics, there's one facet which is often very understated and gets missed not only by students but perhaps by people who are very experienced in the area, which is that you might sometimes wonder that the equations which are there, and as you go, some of you have done the course, some of you might be kind of in the process of migrating through it. The underlying equations, if you kind of observe, they are the same, and we say that they kind of apply to all electromagnetic phenomena, right? So no matter what particular type of material you are studying, it's a set of 4 equations, which describes everything. So you kind of keep wondering, what is it that really differentiates one type of material from another type of material? And electromagnetic theory is a very interesting way of bringing that thing into the theory, which kind of goes by the name of what are called as constitutive relations. And you would have studied the most simplest one of those, where you would have heard things like B is equal to epsilon E, B is equal to mu, and so on. Almost in a formulaic way, you would have kind of remembered them. But what gets often missed out, right, is that there's this entire world of physics that goes into establishing that particular relationship. Often, deep aspects of the underlying quantum mechanics of the material goes into telling that, okay, this particular material is going to have this kind of constitutive relationship. And you can do the entire electromagnetics of that material, how electromagnetic waves might propagate through these materials, without at all bothering about what exactly went into establishing that little, that simple constitutive relationships, which, experimentalists spend a lot of time setting up experiments to establish those, and theorists spend time modeling those, understanding from basic principles how such constitutive relations may come about. And this aspect of how physics at one scale separates from physics at another scale is an extremely fascinating area. And this whole subject of quantum field theory also is contained in there, right? I mean, have you thought about this? That when you study, for example, something like hydrogen atom, right? In the formulation of the problem, you probably just describe a nucleus and then there's an electron moving around it. But it might be kind of bothering you that at the end of the day, there is so much thing happening inside the nucleus of an atom. Doesn't something about what's happening inside the nucleus of the atom affect what happens at an atomic level? So a first order approximate answer to it really doesn't. All that you need to know is what is the nuclear charge, or perhaps what magnetic dipole moment the nucleus possesses. So in some sense, the things that happen at a much smaller length scale is completely decoupled from what happens at a slightly larger length scale. And this ability to separate scales is something that actually makes life a lot simpler for us, right? A lot of you who have passion for electrical engineering would also know this, and I kind of figured this out while I was teaching this course on electromagnetic fields and waves, that when you are looking at a simple electrical component, right? Physicists would spend a lot of time thinking about, why does a diode get the IV characteristic curve that it gets, or another component may have a different IV curve. But once you get at the level of circuits, you don't have to worry about what happens at a single component level. You can simply take the IV curves of different components and you wire together circuit, and very simple equations can help you analyze that. And you take such a circuit component and put it as a part of a bigger system, you only need to worry about input-output of that little box. And so this kind of separation of scales is even seen, and it's sort of, why at some level, success, we've been able to achieve a lot of success in, varying domains of science, engineering, and technology. What I do as a part of my research, and Mrinmoy, who is here, is right at the corner over there, and I'm kind of exploring, a set of problems with him, is quantum field theories, or in general field theories from your experience with electromagnetic theory, you would know is that electric fields and magnetic fields essentially correspond to a set of numbers, one for every point in space. So inherently, when you are trying to address a problem in quantum field theory, there are just a huge number of variables involved in the problem. And the problem computationally can start becoming very intractable. So we would like to make it tractable, and to achieve that, we, from these large number of degrees of freedom that you have, you just need to be able to find the right set that you can work with from this infinite collection, which will be a good enough approximation to what the full theory would predict. And we use this feature heavily there, that physics at different length scales will decouple. Okay, this does not always happen. One of the places where it shows a violation is exactly, for example, in the physics of second order phase transitions. When a paramagnetic material becomes a ferromagnetic material just around that region, you see that physics at varying length scales tend to couple with each other. But barring those, this kind of decoupling is seen very commonly. So what we are trying to do as a part of those problems is that we look at different types of models of field theory. So electromagnetic theory is one example of that, but we're looking at it from a quantum mechanical perspective. And we want a natural language to be able to understand length scales. And so we've been using a class of functions which have history in, their initial use was quite heavy. I mean, it still continues to get used very heavily in the domain of signal processing in communication, electrical engineering. They go by the name of wavelets. There are a variety of different wavelets which are known. But the one which we're currently focusing upon are called as Debauche's wavelets. So one of the interesting things about Debauche's wavelets is that these functions, they are non-zero only over a small length scale. Okay, only over a finite length scale. I shouldn't say a small length scale. They are non-zero over a finite length scale, and you can construct a full basis set out of it, so that any square integrable function can be expanded in terms of those. So it allows you to build a very natural language to talk about what your underlying length scales are and be able to talk about how do you separate the length scales. And so the current work that we are doing is looking at simple prototype quantum mechanical models and quantum field theoretic models. And using this language of wavelets, try and figure out how this separation of scales would happen and how a particular theory, which otherwise looks like a collection of a very infinite number of degrees of freedom, could be effectively represented by a system, right, which contains a much lesser number of degrees of freedom, and so computationally is much more tractable. So this entire area is an area of passion for me, is because I just enjoy the methodology of physics, the manner in which we solve problems in physics, right? And there is a whole slew of problems. Usually, you often find people passionate about a particular application area, and people kind of use different methods to kind of attack an application area. But over the years of looking at a variety of different quantum field theories are pervasive, from condensed matter physics. You can see them in atomic optical physics, high energy physics, variety of areas. Quantum field theories are seen, and different methodologies are used. I'm very passionate about those methods, and so right now, kind of following along those lines, I'm looking at the use of these so-called Debauche's wavelets in helping us build effectively simple, descriptions of those same theories to kind of be able to solve them. So we're looking at some prototype problems where we kind of understand through other methods how the physics of that model really is. We're using these Debauche's wavelets to kind of see whether it offers any improvement in terms of how we computationally address those problems before taking them and applying them in areas such as quantum chromodynamics, right, which is also a field theory in itself, which has been traditionally or computationally an extremely difficult problem to address. So that's sort of what I do. I am mostly available in the office, so those of you who are interested in kind of chatting up with me are more than welcome to drop by. Also, occasionally, if you just kind of in your early stages you want to know what field theory is, you can also kind of attend some of the early classes that I do when I teach that course, so that you'll also get a feeling for how that course is. Also, the video lectures are because we've been kind of recording these video lectures very commonly. So I mean, those of you who may kind of want to take a look at that as well, you can just mail it to me. I can share a link with you, so that a couple of early lectures will give you a sense of what that discipline is all about. So, yeah. Thanks, guys. Thanks very much. Also, I'll be available during tea for any additional interaction if you want. Thanks.
Okay, so we are just arranging this now. Okay, so you can.
No, you can have time. I'm waiting for my child.
I'll just check if they've arranged it.
Okay, so we can discuss over chai also. Okay, so okay, I'll tell you very briefly. Since it is everybody's board. So basically, what we do is we just play with optics and lasers. That's our main job. And on the way, we see some physics also. So mainly, we wanted to see initially when we were here, we wanted to see things happening at the microscopic level. So what we did was we constructed
different types of optical microscopes. And we started looking at certain systems, especially biological systems. So we wanted to see, for example, how molecules or biomolecules travel through cells. Cells means biological cells, and to the nucleus, cell nucleus, how molecules travel. Okay. So one of the problems, for example, Gaurav is going to give a talk on Monday. Monday there is a department seminar, I think, Monday, 12 o'clock or something.
Yeah.
11 o'clock. 11 o'clock we have a department seminar. So Gaurav is talking about how these viruses, for example, enters the nucleus. So by the way, the nucleus is very protected kind of stuff. It doesn't allow everybody to go in. Okay. But these viruses are able to manipulate and enter the nucleus. So in the lab, what we try to do is we try to see such things, how such a molecules enters the nucleus. So Gaurav is, for example, going to talk about the mechanism, so the methods by which this virus cheats the nucleus and enters the cell nucleus and reproduces itself. Okay. For example, how the coronavirus is able to enter our cell. So in biology side, we look at such things, and so mostly as an experimentalist, we are interested to, we get the kick out of measuring something which is very challenging, detecting, seeing something which is difficult to see. For example, these are all things which we cannot normally see, right? So we develop techniques for that, and we get the kick out of it. Another thing which we recently started with Manoj likes to play with photons. So he's doing interference with photons. He wanted to do what Nadia want to do with some foundational problems on quantum mechanics, check quantum mechanics with photons. So that's another thing which very recently we started doing. And these are challenging stuff. It's not easy to detect a photon, for example. So I can talk about it, but you won't get a feeling. Okay. So you will get a feeling only if you come to the lab. If you come to the lab and see how you can detect a photon. Okay. And how you can see photons interfering. Okay. How you can use these photons to see some of these principles of quantum mechanics. So probably rather than my talking so much, best thing is that, okay, there is a place, time for lab visits. Just visit the lab and see what is happening there. So we have a reasonably good optics lab. So you'll be able to do all kinds of things. Whatever you can think of, you should be able to do in the lab. Okay. So if you want to do any particular, it need not be related to what I am doing. If you are interested in doing some experiments in optics, you can always visit the lab. You'll make so if some components are missing, you can buy all these. Okay. So just come to the lab, talk to the students, talk to me, and try to get a feeling of what we are doing. Okay. Thanks.
Thank you.
Yeah. Yes, you speak, we not have that.
Good evening to everyone, and thank you for this organizing physics week. So this is Chandradev Sarma. I did my PhD in high energy physics, and then slowly I developed my interest to understand the complex system. So actually, I wanted to understand the stock market. I think many of you are interested. So can we apply physics to understand the stock market? So I think seriously I started learning in 2010. So I joined in 2009 and then I started learning. Then initially I was thinking it's a weird idea. So there is no relationship between physics and the stock market. Then physics, we understood many things, just like a second order phase transitions, and then we have a stationary system, and then quantum field theory. We generally start with Fourier transform. So Fourier transform, basically the problem is, I think, if you have non-stationary, non-linear thing, then you cannot capture many things with the help of Fourier transform.
So do we have any alternative to get some signal? Suppose most people want to know about the crash of this stock market. Suppose you are nowadays, I think many people I think interested in mutual funds, they're investing, but they do not know when to sell and when to enter. So I think Warren Buffett's teacher Benjamin, I think he was knowing when to enter, but he was not knowing when to come out. Then Buffett put lots of effort. But then I wanted to understand, can we apply physics to get some idea? Then I got, then I realized, okay, it's like a Langevin equations, Boltzmann equation, many non-linear, non-equilibrium systems we have in physics can be applied here. And if you observe carefully, then again you can see a cycle in a stock market also going up and down. Then, because whether we are really irrational or we are rational, just like a physics and chemistry, we have a well-defined equation. Based on that, you can simulate and can get idea. But here situation is very complicated because it depends on our mood, some rumors, informations, GDP, interest rate, many parameters are there. But in physics, if you know that if you have more than 4 parameters, that is not physics. That means you are just fitting data analysis. So can we, suppose we have even 1,000 or million or billion parameters, can you bring it to level 4 or less? If we have 4 effective parameters, then based on that, I think we can make a model and we'll try to understand. Okay, so market is very unstable, dynamically very unstable. That means we should not invest this time. We cancel. So can we get any early signals? So then I was studying, and then we are finding, okay, so Fourier transform may not be a good idea. Then what is the best technique? So because Fourier integral will give you, just like a fast Fourier technique, can give you some frequency domain. You can get various type of frequency and then see what is the strength. Based on that, you can get some signal. So that's why quantum field theory basically we assume that solution is Fourier integral, and then we are just imposing it. We are getting green function, many things. Then here I found wavelet is very interesting. So if you apply wavelet, then I think you can separate this length scale, and then you can say it's a daily, monthly basis, then quarterly basis, monthly, yearly basis, and then you can see the trend, and you can capture some part of it. And then for the time being, for example, in the stock market, if you observe price earning ratio, price book value, and so on, many parameters are there. But if you get 4 such parameters, and based on that you fit some wavelet, suitable wavelet, then I think we can get some early signal. But I think that is also very subjective. So far I am still struggling, but mostly I think I published 2 papers based on that. So one is just like the largest eigenvalue of entire market, just like a Sensex or Nifty. So giving you some idea about entire market.
And apart from publishing, how much money you make?
I was just scared, so I was learning. So before investing, we should understand. But two students got really good job in Hud House, and they're enjoying there. So these 2 people helped them. So right now I'm struggling to get such 4 parameters. Once we get 4 parameters, we can fit into wavelet, and then we'll separate into various length scale, and then we'll tell that, okay, if you understand these 4 parameters, then I think
separate millionaire from billionaire.
that would be good. So I think for you, I think maybe very beneficial, because I think nowadays I think many people are exploring machine learning, data science, etc. And fortunately, last semester I taught data structure and algorithm, and then statistical method and applications. So data science, etc. I am learning all these stuff so that I can put everything to figure it out. And then most probably I think we'll try to understand. But it's very challenging. But okay, let us apply some physics. But according to Professor Elike, it is saying eco-nano-physics. That means there is no physics in this. So I agree with him. But anyway, it's a challenge. Let us try. So thank you.
all the snacks and everything is ready. You can have tea. There's aloo vada.
What's after that?
After that, we have a quiz lined
When do we
up.
come back?
Immediately, like whenever we're done. But,
Is it given after 20 minutes?
yeah, yes. Can we continue in a second?
What the process is all doing?
अच्छा एंड किया तो फिर there's going to be I think not. Can you not pause it? I don't think so. तो फिर